Alright, today we're going to walk through our Newton's laws or forces test review. Starting off, here are the equations that will really be given. One thing to keep in mind is that we'll be using an equation sheet, so we'll also know that the force of gravity is the weight. Weight and force of gravity are the exact same thing. Okay, so number one, let's just make sure we're still recording. Perfect, I'm paranoid. When some total force is applied, an object has an acceleration of 5 meters per second squared. If the same force is applied, but the mass is decreased by half, calculate the new acceleration of the object. Okay, well, we have the equation right up here. Total force is equal to mass times the acceleration. Let's write that out. So, we are keeping the force the same. The mass goes down by half. Calculate the new acceleration. Well, the only way this is possible is if the acceleration doubles. The mass decreased. So if you just think about a real world example, say you're pushing on an actual physical car. The car's not really going to move very much. If it is, say we take the car push lab, you push on the car, it's in neutral, it moves. That's awesome. But what if you applied that same force that you apply to the car to a little toy car, right? The little toy car would go a lot faster. Its acceleration would be a lot greater because if your mass goes down, well, for the same total force, your acceleration must go up to compensate. And it's proportional. So if the mass goes down by half, the acceleration doubles. If the mass was a third, the acceleration would triple. And this relationship keeps going. So we know, okay, the acceleration should double, the acceleration would be 10. There's actually another way to solve this. Whenever you're given problems like this, and this happens on the ACT a lot, you can make up a number and just run with that number. For example, if some total force is applied, we don't know what total force, but let's just make one up. Let's say the total force is 10 newtons, a number that's nice and easy to work with. Say we have that, right, 10 newtons. Then all we'll do is we'll take our equation, we'll say, okay, our total force is 10 newtons, plug in some mass, let's say our mass, actually, well, really we have the acceleration. So we'd plug in this, we could solve for the mass. We know, okay, the mass in that situation is 2 kilograms. The situation that we just made up, where we said, okay, imagine this is 10 newtons. Then we can go ahead with this mass and say, okay, now that we know this, do that same equation again. We're applying the same force. It's still 10. Our mass is 2. In our original situation, our mass was 2. But now, the mass is decreased by half. So this should be 1. We could solve for the acceleration. Lo and behold, that acceleration is 10. It's the same answer, just a different way to get it. Number 2, can an object move with a constant speed while experiencing an unbalanced total force? Yes, it can. Constant speed. This is the key. Speed is just how fast you're moving. Velocity is how fast you're moving and the direction you're moving in. Take the moon. Right? If we draw out, say, here's the Earth, and we have going in an orbit, roughly a circle, around the Earth is the moon. Well, the moon has a bunch of different velocities. It's at a constant speed, approximately, but the velocity changes direction. Say it's going clockwise here. The velocity points different directions as it goes around and around. So the velocity is changing. The magnitude of the velocity, the speed, doesn't change, but the direction does. So you can't have a constant velocity while experiencing an unbalanced total force, because unbalanced forces cause acceleration. Acceleration is a change in velocity, but you can have a changing velocity, but a constant speed if your direction changes. So yes, it is possible to move with a constant speed while experiencing an unbalanced total force. 3. 60-kilogram woman sits in a chair. Draw a free body diagram and name the Newton's third law force pair for each of the forces acting on the woman. Okay. Here is the woman in the chair. The woman would have a force of gravity, and there would be a normal force. Name the Newton's third law force pair for each of the forces acting on the woman. Okay, so here, our normal force. This let's add in some extra details. This is really the normal force. The chair, whoa, going crazy here. This is the chair on the woman. There would also be, if we had the chair, we know there should be some opposite force of the woman acting on the chair. If we look at this force of gravity, this is really the Earth acting on the woman. The paired force would be the woman pulling on the Earth with her own force of gravity. Alright, excellent. Let's even go ahead and add in these forces. They're equal and opposite. They're not a third law pair, though. The pair, again, would be the normal force of the woman pushing on the chair. This would be downward. And the pair for the Earth pulling the woman down would be the force of gravity of the woman pulling the chair up. Not the chair. I am misspeaking. That is not correct. The woman on the Earth pulling the Earth up. So even though these forces are balanced, the normal force and the force of gravity, they're not a third law pair. Alright. Number 4. Free-body diagram to the right represents the forces acting upon a rightward moving object. Circle your answers below. Here, I like to draw in a little arrow. Just say, okay, we're moving to the right. That helps us. Okay. Is this object experiencing balanced forces or unbalanced forces in the left/right direction? So horizontal, in the x direction. Well, in the x direction, we have a force to the left, a force to the right. The force to the right is bigger, so we certainly have unbalanced forces here. B. Balanced or unbalanced in the up-down direction. This is the y direction. Well, they're balanced. Right? They're the same size, opposite directions, they balance out. Is the object getting faster, slower, or moving at a constant speed? Super important. You cannot tell what way something is moving from the free body diagram. If we just gave you these two free body diagrams that you see, the one right here and the one right here, those are the exact same. You don't know what way the object is moving unless we tell you. Right here. So, we know this object's moving to the right. We know from the free body diagram that the acceleration is to the right, because you always have an acceleration in the direction of your unbalanced force. That unbalanced force is what causes the acceleration. So if you have a velocity and an acceleration in the same direction, you are speeding up. You're getting faster. Then we say, okay, same free body diagram, but now the object is moving to the left. So we have a velocity leftward. We know the forces are unbalanced in the x direction. They're balanced in the y direction. But since we still have that rightward unbalanced force, we have that rightward acceleration, the acceleration and velocity point opposite directions, that will always mean we are getting slower. Alright, on to our next page. Draw a free body diagram of a box sliding on a rough surface coming to a stop. Alright, lovely. Let's go ahead and do that. What we'll say, here's our dot. It is on Earth, so let's draw in a force of gravity. It is on a surface, so there's a normal force. These are going to be balanced. It's not accelerating up or down. But there is friction. It is on a rough surface. That's our identifier for friction. It's coming to a stop. So, really, this object's moving to the right. Friction is opposing motion and it's slowing down. The forces are not balanced because it is accelerating, it's slowing down. B. Box being pushed across a rough surface at a constant velocity. Here we go. On Earth, force of gravity. On a surface, normal force. These are balanced. It is being pushed, so there is an applied force, and it is at a constant velocity on a rough surface. The rough surface gives us friction. The constant velocity tells us that friction should balance with our applied force. Constant velocity, no acceleration, means balanced forces. So, forces are indeed balanced. Hockey puck sliding across an ice rink. Ignore friction and air resistance. Okay? Well, no one's actively pushing it. There's no applied force. It's still on Earth, so there's gravity. It's on a surface, so there's a normal force. These are balanced. The hockey puck's just sliding across an ice rink. It's not accelerating up, not accelerating down. Balanced forces. Hockey puck at rest on ice rink. Also, balanced forces. No one's pushing it. There's no friction, no air resistance. We just have gravity and normal force. And they are balanced. Notice how these free body diagrams are the exact same, but the movement is different. You cannot tell motion from a free body diagram, only acceleration. Alright. 7. A 0.166 kilogram hockey puck slides across frictionless ice at a constant velocity. Determine the acceleration of the puck in the horizontal direction. Explain why this answer makes sense in one sentence. Alright, so here we have a hockey puck sliding. There's frictionless ice, so you want to be careful with that. We're ignoring friction. We're also told to ignore air resistance. Determine the acceleration of the puck in the horizontal direction. Well, it's at a constant velocity, so the acceleration must be 0. For an object that's at a constant velocity, that means no acceleration. And that's really it. No math needed. Number 8. Person pushes a 20 kilogram hockey goal across frictionless ice with a constant horizontal force of 10 newtons. That's a free body diagram. While the person's pushing it. And we're doing it of the goal, not of the person. Well, there is a force of gravity that is downward. There is a normal force. Those are going to be balanced in this case since the object's not accelerating vertically. And they are pushing it across frictionless ice. So there will be some applied force, like so. Okay? Then, calculate the acceleration of the goal. We drew the free body diagram. What is our unbalanced force? Well, let's get a few equations out here. We know the total force is equal to mass times the acceleration. But the trick is, let's identify our unbalanced force. Our unbalanced force is this applied force. Normal force and gravity cancel out. So we really know that this total force is just going to be equal to the applied force. So what we can do, substitute this in. Plug in the applied force for our total force. And rewrite to get the applied force is equal to the mass times the acceleration. This way, we know that applied force, it's our 10 newtons. We can write in 10 newtons, plug in our mass of 20 kilograms, solve for our acceleration, divide 10 newtons by 20 kilograms, we get our acceleration. This would just simply be 1/2, or 0.5. 0.5 meters per second squared is our acceleration. Now, technically, you could keep the units as newtons over kilograms. Those are valid units for acceleration, but much more commonly, we just see meters per second squared. So we're just going to use meters per second squared. These are equivalent, newtons per kilogram and meters per second squared. They are the same. What is the force of gravity on the goal? Well, we have an equation for force of gravity. Keep in mind, force of gravity is weight. We could also be asked what is the weight of the goal, and they would be the exact same solution. Force of gravity, or the weight, is equal to m times g. The mass is 20. The acceleration is 9.8. We plug in, and we can just go ahead and use a little calculator. 20 times 9.8 is going to give us 196. What's our unit? Well, it is a force. Every force is measured in newtons. Alright. Number 9. If a waiter is walking through a restaurant with a tray full of water and comes to an abrupt stop, the glasses will fall forward off the tray. Is there a mysterious force that pushes the glasses forward? Explain why this occurs and whether the mysterious force exists. Well, let's talk through it. There is no mysterious force. People would like to say there's, this force of inertia, but does not exist. Force of inertia, that is not a thing. It is the object's inertia that is what keeps them moving. It's what resists a change in motion. So the waiter and the water were in motion moving forward in a straight line. The waiter stopped because they applied some force to the ground that made them stop when the ground pushed back on them. But there was no force on the water. The water just kept going until it hit the ground where some force made it come to a stop. Number 10. An EVA suit, also known as a spacesuit, has quite a large mass. Spacesuits can have masses up to 115 kilograms. Calculate the force of gravity that acts on the suit while it is on Earth. Okay, force of gravity, aka the weight. Force of gravity equals m times g. We know the mass of the suit, because it is what acts on the suit. 115 kilograms. 115. I'm going to drop our units to save some space. Times 9.8. Pop that into your calculator. You get 1127 newtons. Forces in newtons. 8. Astronaut steps off the moon lander onto the surface of the moon. Acceleration due to gravity on the moon. The g value is 1.6 meters per second squared. Calculate the weight of the spacesuit on the moon. Weight is force of gravity. We're doing m times g, but now we still have the same mass, 115 kilograms. That doesn't change when you go to a different planet. What does is that g value. Acceleration due to gravity, it's now 1.6 on the moon. Plug this in, we get 184 newtons. Mass of the suit on the moon. Mass doesn't change. Mass is still the 115 kilograms. The 85 kilogram astronaut wearing the 115 kilogram spacesuit is standing on Earth. Determine the normal force acting on this astronaut from the ground. Well, let's draw a free body diagram. They are at rest on the Earth. They must have balanced forces. One force acting on them is gravity. Another force is the normal force. This is it. No applied, no friction, no tension. For them to be standing still, they need balanced forces, no acceleration. So, the normal force must equal the force of gravity. We know we have an equation for the force of gravity. Force of gravity is m times g. So in this case, since the normal force is equal to the force of gravity, the normal force must also be m times g. Now we are back on Earth, so our g value is 9.8. So when plugging this in, we need the combined masses. We need the 115 plus 85. Because we are calculating the normal force acting on the astronaut and the suit from the ground. So, 85 plus 115 gives us 200. That's our mass. Multiplied by our g value of Earth, 9.8. And we get 1960 newtons. 8. Total mass. Well, mass doesn't change, so that is just our 200. The mass of the astronaut and the suit, just add them together. 200 kilograms. Mass is measured in kilograms. You push a stack of physics textbooks across a table. What else would you do with them? So real. The force of friction between the books and the table is 8 newtons. Books have a mass of 15 kilograms, and they accelerate at 0.2 meters per second squared while you push. These are some really great practice problems. Highly recommend you practice and are comfortable with them. Here is our dot representing our object. Draw the free body diagram of the stack of books. Well, they're on Earth. We have a force of gravity. They're on a table, a surface, so there's a normal force. The books are not moving up or down. They're not accelerating up or down, more importantly. So we know our vertical forces must be balanced with each other. We're pushing them to the right. We have some applied force. And there's some friction. We know they're accelerating. They're going to accelerate in the direction of the push. So I'm intentionally making that applied force bigger than friction to be unbalanced. Calculate the horizontal total force on the book. Well, we have our equation for total force, Newton's second law, but this isn't enough. Actually, it totally is. In this situation, we can use the mass and the acceleration to solve. We're given 15 kilograms, 0.2 meters per second squared. We can just use them with our force. Let's plug them in. Mass 15, acceleration 0.2, multiply, and we get our total force 3. That is a horrible 3. 3, slightly better, 3 newtons. Calculate the applied force on the books. This is what I was thinking of earlier, where we need to not just use Newton's second law, right? That is just F total equals mass times acceleration. The applied force doesn't show up in that equation anywhere. When we're calculating some other force that's not gravity, we need to make our own equation for our total force. We know the total force is just the positive forces minus the negative forces in a particular direction. Vertically, they're balanced, so we're just looking at the x direction. So the total force in the x direction is the applied force minus our force of friction. With this equation, we can plug in that total force that we just found. 3 newtons. We could even rewrite, if we wanted, the entire equation and say, really, replace total force with mass times acceleration is equal to the applied force minus the force of friction. Mass times acceleration gives us 3 equals that applied force. We are told the friction is 8 newtons. Plug that in. We're going to do a little bit of algebra. Add our 8. They cancel. And then we get 3 plus 8, 11 equals our applied force. And in particular, this is, cannot forget our units. Let's scooch that on over, 11 newtons. Really, what I want to highlight with this problem is all of our questions, it is a good idea to draw your free body diagram, write out Newton's second law, and then write out your custom equation for the problem. Generally, we'll have one of them, you will be given the variables you need. So you will either have the mass and acceleration, and you can use that to find the total force. Or you'll have the applied force and friction, and you'll use that to find the total force. Whatever total force you find, you're going to use that, and you're going to plug it into the other equation. So here we found it with mass times acceleration. We plug it in here to find our applied force. Let's see what we have to do in our next example. We're going to start out with our free body diagram. 2 children push a 15 kilogram box in opposite directions on a carpeted floor. The bigger child pushes with 20 newtons of force to the right. Small child pushes with 10 newtons of force to the left. An unknown frictional force opposes the motion of the box. The box accelerates at 0.2 meters per second squared. We have to use a lot of our knowledge here. We know we're on Earth. Gravity straight down. Normal force balancing it. The fridge is not accelerating up or down, must be balanced vertically. Let's continue. One child is pushing 20 newtons to the right. So let's draw a big force. This is an applied force to the right. We can even label this. This is maybe our first applied force. And then the smaller child, they're pushing to the left. Half as much force. We'll label this the applied force 2. Some unknown frictional force opposes the motion of the box. Well, if we look at this, what way would the object accelerate? It would accelerate to the right. So, friction is opposing that motion, acting to the left. So let's draw that in. Here's our force of friction. This way, we want to calculate the force of friction acting on the box. This one's involved. Here, we're going to use essentially what I was talking about earlier. Let's write out our equations. We know the total force is equal to mass times the acceleration. But that gives us the total force, which is great, But we're not asked for the total force. We're asked for the force of friction. So, what equation can we write that has the force of friction on it? We can write a custom equation saying the total force is just the sum of the forces in a direction. Vertically, they're balanced, so we're going to look horizontally in the x direction. We have the first applied force, that's in the positive direction, but we're going to subtract our second applied force, that's in the negative direction. We're also going to subtract friction, because it's also acting in the negative direction. Here, our friction shows up. This is great, but we don't have our total force. This is where we need to substitute in one equation for the other to solve. Set your two equations equal. The mass times acceleration, which is the total force, is equal to all of this. So plug this in. Replace F total with mass times acceleration. Rewrite mass times acceleration equals the applied force, 1, minus the second applied force, minus our force of friction. And go ahead and plug in all our information. The box has a mass of 15 kilograms. We know the box accelerates at 0.2 meters per second squared. The applied force of the bigger kid is 20 newtons. The applied force of the smaller kid is 10 newtons. Friction is our unknown. Just like that, this really hard question, we just have to do a little bit of math. 15 times 0.2 gives us, I believe that's 3. Let's double check on a calculator. 15 times 0.2, 3. Excellent. Equals 20 minus 10. Let's just simplify that. 10 minus our force of friction. Let's go ahead. Let's move friction over and subtract by 10. If we do that, we get force of friction. Now it's positive because we moved it over. 10 minus 3 gives us 7. So the force of friction is 7 newtons. Determine the strength of the force from the box on the larger child. Well, the child pushed on the box with a force of 20 newtons, so Newton's third law says that the box must push on the child with 20 newtons. Newton's third law. Same thing for this smaller child. Smaller child pushes on box with 10 newtons, box pushes on smaller child with 10 newtons. Alright, let's go ahead and do this next problem. Number 13, Santa's reindeer tow an 800-kilogram sled along the ground. Reindeer can't really fly. Shucks. With a force of 500 newtons. The friction force on the sled is half the pull force, and the air resistance force on the sled is half the friction force. Draw a free body diagram. Okay, well, there's still gravity. They're not flying, so there is a normal force. These are balanced. They don't have to be. It just so happens the object's not accelerating up or down, so they are balanced. Then we say, okay, the reindeer are towing this. So here, this would really be a tension. They're towing it with some rope or cable. Friction force on the sled is half the pull force. So let's draw half. Okay, this is our friction. And then air resistance is half the friction. Let's draw half of that. This is our air resistance. Okay, let's go ahead. We're going to use our same technique. Write out your two equations for the total force. One of them is just Newton's second law. The other one, you just list out positive forces minus negative forces. Tension is positive, friction is negative, the air resistance is negative. The way we tell is just the direction. Anything that's to the right is positive, anything left is negative. If we were dealing with vertical forces, anything up is positive, anything down is negative. Now go ahead, plug them in for each other. We get that the mass times the acceleration equals Ft minus Ff minus F air. Plug in the mass of the sled, 800. Do we have the acceleration? No, that's what we're finding. So we'll leave it as a variable. The tension is 500 newtons. Friction is half of the tension, so 250. Air resistance is half of the friction, so 125. Go ahead and solve. Our right-hand side is just 125. equals 800a. Divide both sides by 800, and we get the acceleration is 125 divided by 800, 0.156 meters per second squared. Alright, last problem. You, 75 kilograms, just landed from a jump off the bus and felt a little sting in your knees. Ouch. When you landed, you were moving downward at 3 meters a second and stopped completely in 0.08 seconds on the ground. Calculate the normal force felt by your feet during this time. Well, here we're going to use some kinematics. Right, we have a time. Let me turn on my pen, that would help. Time 0.0. What? There we go. 0.8 seconds. We know the initial velocity when we hit the ground was 3 meters per second. Our final velocity when we're coming to a rest is 0 meters per second. We want to, and we have our hint, let's find this acceleration. Because then we can take that and plug it in to Newton's second law. F total equals ma. We have the mass. If we find the acceleration, we can find that total force and use it to find the normal force. The way we'll do that is we have our free body diagram. We know the forces. While we're accelerating upward, we have a larger normal force than our force of gravity. So let's actually go ahead, let's make this force of gravity smaller. The normal force is bigger because we're accelerating upward when we're hitting the ground, when we're coming to a stop, moving downwards. Okay, let's find this acceleration. We are missing a delta x, so let's go ahead and use our handy-dandy kinematic equation. Vf equals Vi plus At. Final velocity is 0. Initial velocity is 3. The acceleration is what we're finding. Time is 0.08 seconds. Now we just have to go ahead, calculate. Let's find our acceleration. 3 divided by 0.08 gives us an acceleration 37.5 meters per second squared upward. The upward acceleration is caused by an upward total force. We can write out, using our free body diagram, the total force is normal force minus our force of gravity. So we'll just go ahead and we will say, with our acceleration, plug this on in. Total force is mass, 75 kilograms, multiplied by our 37.5 acceleration. That gives us a total force of 2,812.5 newtons. We can then take that and plug it in here. So our total force, 2,812.5, is equal to normal force minus the force of gravity. Force of gravity is m times g. The mass is 75. G on Earth is 9.8. We get a force of gravity 735. Plug that in. Now we get 2,812.5 equals normal force minus 735. Add 735 to both sides. And we're going to get our answer. Normal force, 3,547.5 newtons. You'll notice on our answer key, we just rounded that up. 3,548 newtons. As you can see, a lot of this unit is starting off where you're looking for, right? We're looking for the normal force. We can't find the normal force. Normal force shows up in our equation right here. But we didn't have the total force. We had to work backwards. We also didn't have the force of gravity. We had to find the force of gravity. We had to find the total force to solve.